Hello and welcome to lecture 7 in transformation, semigroups and applications. I'm Imam, a senior lecturer at the Department of Mathematics, Ahmad Bello University, Zaria. In this lecture, we are going to talk about gravity of alpha in finite full transformation semigroups. So we define what we mean by gravity of alpha. For each alpha in Tn, Tn being the semigroup of all finite full transformation on a set X, n of 1 to n element, we define the gravity of alpha to be the integer g alpha, which is equal to n plus c alpha minus f alpha. Here c alpha is the number of cyclic orbit of alpha, and f alpha is the number of fixed point of alpha. We have defined this in lecture 6. We have a theorem concerning the gravity of alpha. In 1980, Harvey proved the following result. If Sing n denote the semigroup Kn n-1, which is the entirety of Tn but minus Jn. Jn is a set of all elements of height n. That is the permutations. So from the full transformation semigroup, if you remove the permutations, you are left with the non-singular set mappings, and that set is denoted by Sing n, and that is Kn n-1. We have already shown in the last lecture that this thing is an ideal of Tn, and so therefore Sing n is a subsemigroup. So if we donate by Sing n Kn n-1, then the maximum gravity over all elements in Sing n of height r is equal to n plus a half into r minus 2, where here we take the ceiling. This is the flow function of the integer, that is the least integer function, because this fraction may turn out to be a rational number. So whenever it is a rational number, one will take the closest smallest integer closest to the number. And also the maximum gravity over all alpha in Sing n is equal to 3 all over 2 into n-1. Again, the flow function of that. So this lecture will be dedicated to discussing the proof of this particular theorem. So to prove this result, because we are looking for the maximum gravity, so let's say we are now trying to find among all the elements of height r, so what is the maximum gravity? And this is what we are doing here. To do that, if you look at the definition of the maximum of the gravity of alpha, if you want to maximize this particular quantity, since you are adding n is fixed, and you are adding the number of cyclic orbits and subtracting the number of fixed points, so you have to maximize the cyclic orbit while keeping the fixed point as small as possible. So to maximize the gravity, we must make sure that the cycle of alpha is made as large as possible while keeping the fix of alpha as small as possible. And to do that, we maximize, if you want to maximize the cycle of alpha, you use 2 cycles, because you are having point, so a cycle formed by 2. If you use 2 cycles exclusively, then you maximize the number of cycles. And so if r is odd, greater or equal to 1, then we can use r minus 1 all over 2 cycles. So because we want to have r element in the image then. So let's say you identify 1, 2, 3, 4, 5, 6 up to r element, which you want to form an image. The way to do it, if you want to get a maximum number of cyclic orbit, then you have to pair the element 2, 2, 2, 2, 2, 2, the image set. So you would have to say 1 is mapped to 2 and 2 is mapped to 1, and then you pair the element to form 2, 2 cycles. The last point, since R is odd, cannot pair with any point, so you have to fix it. And then the remaining element of the domain of alpha, R plus 1 to n, you allow them to map to R. And this will give you an element of maximum number of the cycle orbit and the least number of the fixed point. There is another way one can do it. You can avoid having a fixed point. We are going to do it in the next slide. But to do that, you would have to sacrifice one of the fixed points, but that will not change the gravity. For this configuration, the gravity is n plus the cycle of alpha minus 1, which is the fixed point, because you have only one fixed point here. And you have r minus 1 over 2 cycles. And this integer, if you simplify, it is this, and that will give you the required formula. And then an alternative way to do it, if r is greater or equal to 3 but still odd, then you can reserve 3 of the point of the image and then form 2, 2 cycle, that is r minus 3 2 cycles, and then the remaining 3 you allow them to map in a cycle form and map the remaining point of the image of the domain of alpha to one of this, to r here, see. And still this is giving you a cycle, the number. This is not actually the maximum number of cyclic orbit, but it does it in a way that there is no fixed point. So you avoided a fixed point so that you would not have to subtract any one. But then at the you had to sacrifice one of the cyclic orbit, and so therefore you have a gravity of n plus the cycles and then minus 0 because there is no any fixed point here, and this is still giving a gravity of this amount. So in both the two situations of the odd case, we have the formula. Likewise, if r is even, then one can just pair the cycles. You will use r minus 2 cycles, and the remaining 2 points you allow them to map to themselves, and then you now map the rest to one of them. So there is only one unique configuration, and it is the following. It is this particular configuration, because you just have to allow this point that are not in the image to map to one of the points, but you want to avoid a fixed point. So you just have to form 2 2 cycles in this way, r minus 2 all over 2 of them, and then you will now have this remaining last 2 points of the image to map to themselves, and then the other points that are not in the image will map to one of them, say r here. And this will give us a gravity of n plus the number of cycles here minus 0 because there is no any fixed point here, and this is still giving a gravity as the required formula. So, but the second formula, that is the other formula counting the number of gravity for the entirety of the element, not necessarily of height r in sing n, is obtained from this particular formula here by simply substituting r to be equal to n minus 1. And once one substitute r to be n minus 1 in this formula, you realize that the gravity obtained will be 3 all over 2 into r minus 1. But the flow function of that, because the resulting value may turn out to be, on the fraction may turn out to be a rational number, and then you take the flow of that to make sure it is an integer. So this is actually how you maximize the gravity. We will utilize all this information when we come to talk about when we come to discussing the product of idempotent of defect 1 in finite full transformation semigroup. So let me just give an example here. If you consider this particular alpha, we have seen this example before with this orbital structure. We have a standard orbit here and a cyclic orbit, a cycle and a trivial orbit. And then from the orbit, it is clear that you have one cycle and you have two fixed points. So the gravity of this particular mapping will be n plus cycle minus the fix of alpha, but then n is 14, and then the cycles, only one cycle is involved here. You have two fixed points, so minus 2, and that gives a gravity of 13. So this gravity function will play a role in decomposing a particular alpha as a product of idempotent of defect 1. So this is the end of this lecture. Thank you very much for being with me, and I hope to see you in the next discussion where we will start talking about partial transformation semigroups. Please don't forget to subscribe to our channel and watch the previous lectures for better understanding of the subsequent lectures. Thank you very much.